I want to be the very best. No one ever was.
Sing it.
To catch them is my real test. To train them is my cause.
Ba-da-da-da.
I will travel across the land,
We could
searching far and wide. If we can understand the power that's inside. Polar
Pokemon?
graphs.
Polar graphs. Do you know all the words of that entire song? Could you keep going? Let's not keep going.
I think I could if I had like someone else with me who also knew it, and then I was like just typing it or like doing like a sport goal. I think I could do it. Yeah.
How about the second verse? Did you know that the second verse?
Every challenger along the way with courage I will face. That one?
Maybe there's like an entire like there's the theme song, and then there's the song, and there's an entire second verse.
Okay, maybe not.
It's like a 3-minute song. Okay, but anyways, but I have something to show you real quick. Let me turn off my awesome what's it called? A whaleren? Or walren?
Wow.
I don't know. Now I'm second guessing myself. Anyways, let me go ahead and do that because you know what's a great Pokemon? You know what's a great Pokemon?
Am I supposed to guess what your favorite Pokemon is?
It's not a Shuckle. No. It's not a Tentacruel.
Is it a Krabby?
This is a little surprise from Dami. So can you wear this in the next video? You have been grabbed. Look at this stuff, man.
That's really good.
Oh, I wish there was like an Arctic version of a Krabby. The remaking that's a Pokemon they need to do a second version of. Krabby's pretty great. You know what? Krabby, pretty great Pokemon. Kingler, pretty great. What other crab Pokemon are there?
It's like really taxing my Pokemon knowledge.
Really? It really is.
I really I focus on the ones that are adorable, and then that's like pretty much it.
I'm gonna keep my thing off, the background off because I really like these crab things.
That's fair.
So, all right. I love the seal. You know, seal. I think it's hilarious that have all these Pokemon have crazy awesome names, but then seal is just a seal.
It's just seal, but they changed how it's spelled, so it's kind of different.
Did they? So, how do you spell the actual animal seal?
SEAL.
Oh, and seal in Pokemon is SEEL.
Because one of my friends in fantasy basketball had the team name of Seal the Deal Beal, and then his little logo was the seal like from Pokemon, but he had spelled it wrong. Like he had spelled seal as like the animal instead of the Pokemon, and so then part of my trash talk when we were playing each other was like, you spelled that Pokemon's name wrong.
Oh man, lost, that's a shame. That... All right, let's jump into some more polar, hence the Arctic Pokemon, by the way, everyone. Polar equations, graphs of polar equations. You can see the screen, right?
Can you share the doc with me?
I can.
Sweet. And then I think I'll just go through and link Desmos things as we go.
Yeah.
So people can also click on that.
All right, so we are graphing polar equations in this video. And the way we're going to do it, not super exciting. We are going to do a little point plotting. But graphing polar equations can get kind of difficult. So there's a little technique that we can use to help us point plot. But before we start using that technique, let's actually do some point plotting. Let's just plug some stuff in, graph the coordinates, and see what we get. Okay. So the graph of r equals 4 sine theta.
Can we plug in theta equals 0?
Theta equals 0, yeah. So sine of 0 is 0. 0 times 4 is 0. So 0, 0. Let me use a different color. Boom. Awesome. Let's just do the increments that we know. Pi over 6. Sine of pi over 6. The y
pi over 6 is 1/2.
1/2 times 4. It's 2. So pi over 6, we're going to go to 2. Right? And this is a continuous function. We can plug in 0. We can plug in pi over 6. We can plug in all the numbers. between pi 0 and pi over 6. What's happening from 0 to pi over 6 in the sine graph? Like,
it's increasing.
It's increasing, right? So when we talk about increasing in polar graphs, what does that mean?
Does that mean that the radius is increasing?
The radius is increasing. So this is actually happening. We're starting at 0. And our radius is getting bigger. Eventually, we're going to be going like all weird directions. But we have to kind of disassociate what we think of as increasing, going up from left to right. It's no longer that. It's moving away from or towards the pole. And it gets even more complicated when you start dealing with negative radius, because we could be decreasing here if we're going from 0 to -2, even though it visually looks like it's going up. So we got to be careful here. Boom. And then over there on the right, that's Desmos to the graph. Sweet. Awesome.
For checking our work later, not for right now.
Yeah. So pi over 4, it's going to be root 2 over 2 times 4, which is 2 root 2. This is a good one to have a calculator for. Do I have a calculator sitting around? I do. 2 root 2.
I got it. 2.8284.
2.82. Wait, 8284?
Yeah, 2.8284.
We're going to be a little bit closer to 3. We're still increasing. Awesome. How about, let's do pi over 3. That's going to be root 3 over 2, 2 root 3. You got that one too?
Yep. 3.4641.
I'm about halfway between 3 and 4. We are getting bigger still. Pi over 2. We could do 5 pi over 12, but let's just do pi over 2 because it's going to be 1, 4. Oh, we don't need a calculator for that one. 2, 3, 4. Boom. And we're increasing, we're increasing, we're increasing. And then at pi over 2, our sine graph starts to decrease. So we're going to now get closer to the pole again. So 2 pi over 3, I think it's the numbers we already know, right? Sine of 2 pi over 3 is going to be 3.4. And now we're decreasing. We're getting closer to the pole. We're kind of get like sucked in. It's almost like a whirlpool, an attack that Seal, the Pokemon, knows.
Anyway.
Then we're here, and then we're getting sucked in. And then what happens at pi?
Oh, we're back to 0, huh?
We're back to 0, right? Okay, let's see what happens after pi. So I don't like that. Let me fix that. Boom. So look, we made a circle. And actually, if you think back to the last lesson, if we do a little bit of, we multiply by r. We replace sine theta with y. We replace x squared, r squared with x squared plus y squared. We get a circle. And if we do a little bit of completing the square, we can see where that circle is in the rectangular coordinate system. But here we have a circle. Looks like it's centered at 0, 2 with radius 2. What happens when I plug in 7 pi over 6? Let's go all the way from 0 to 2 pi. What is the sine of 7 pi over 6?
Sine of 7 pi over 6 is -1/2.
-1/2 times 4, which is -2. So at 7 pi over 6, we're going to go in the opposite direction too. We're going to be right back here. Let me use a different color.
Oh, are we going to go over it twice?
I think that's all that's going to happen, because we're just going to get the negative of this one, but we're over at 5 pi over 4. So we're going to go in the opposite direction of 5 pi over 4. We're going to end up here again. And then we're going to trace out this exact same circle. And then once we've done 2 pi, we're truly back at the beginning. Because then at 13 pi over 6, it's literally going to be the first to trace. So in one period of the sine function, we trace out this circle twice. Interesting. Cool. All right, so let's go on to the next one. All right. R4 sine, actually, before we do that, just let's clarify. R4 sine theta, or R, let's go ahead and say A sine theta. What is that graph?
That's going to be a circle, and it's how can we describe it? Is it going to be like it's centered on the vertical axis?
Yeah, let's say that. Let's set a circle with y-axis symmetry. It's not system. Symmetry. And what's the radius?
The radius is
Don't confuse it with the r, which is the radial length of the shape from the origin.
The radius is half of the number that we have a. So
a over 2. Yeah, so here it was 2, and then we have y-axis symmetry. Boom. All right, what do you think, just intuitively, what 4 cosine theta is going to be?
Well, I think that that'll also probably be a circle, but maybe with a different kind of symmetry, maybe x-axis symmetry, because we're thinking about the cosine graph.
So for number 2 and for the rest of these, I want to do something that I call an auxiliary graph.
Okay.
And what an auxiliary graph is, by my definition, is I'm going to graph theta versus r, but as if they were rectangular. Like theta is our x and r is our y. We're going to plug in theta and we're going to get the cosine curve. All right, so when I plug in 0, I get 1 times 4, I'm going to get 4. And then at this point, I'm just going to draw 4 cosine theta. We've done this before. Negative 4, 4, 2 pi, pi. Let me throw a pi over 2 in there too. A pi over 4 in there. That's not a pi over 4. What do I want? 3 pi over 2. Let me do a pi over 4 here.
Oh, there you go. Yeah, that's good.
And then I'll throw these dashes in, but I'm too lazy to write the numbers. And I'm going to go ahead and draw a too efficient. I like that. At pi, I'm going to be here. At 2 pi, I'm going to be here. I'm just drawing the cosine curve. Boom. 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 Missed it, but that's okay. Boom.
The sketch.
Yeah. Yeah, that's exactly what it is. Our auxiliary sketch. Okay, so we're going to translate this to our graph. All right, so at 0, we're at 4. And then we are getting smaller. And by smaller, we mean?
Decreasing.
Decreasing. But when we say decreasing with polar graphs, what's happening visually?
It's getting like sucked in.
It's getting sucked in. It's getting closer to the pole. So we're getting closer to the pole. At pi over 2, we're going to be at 0. Right? And let's quickly get that pi over 4 value. That's going to be 4 times root 2 over 2, which, what did we say it was earlier?
2.8 stuff.
2.8. So pi over 4, we're at 2.8. So while visually we're going up, we're actually decreasing. It's a little disorienting, especially first timers. Right, we're decreasing, and then we're actually still decreasing because now we're negative. While we're plugging in second quadrant angles, we're outputting fourth quadrant coordinates because we have a negative radial length now. At 3 pi over 4, we're going to be at that negative 2.8. Negative 2.8. Let me actually be a little bit symmetric. And it looks like you're totally right, by the way. Symmetry around that x-axis. We are still decreasing. We're still decreasing. Excuse me. And then at pi, we are at our lowest point. We're not at 4. We're at the angle pi, and we're at the radial length negative 4.
Mm-hmm.
So we've been decreasing this entire time. And at this point, now we're increasing. We are increasing. And I don't know, can you see I'm like redrawing the circle?
Mm-hmm.
Cool. And then at 2 pi, we're here, and then we start to decrease again. So the first circle we're decreasing, the second circle we're increasing, which is a weird thing to say because the image we see at the end is exactly the same. But different things were happening while we were graphing it. All right. And I think this auxiliary graph kind of helps us see that. And it's going to particularly help when we get into more interesting shapes. All right. But it looks like you're totally right. Circle with x-axis symmetry and radius a over 2. y, not y, r equals a cosine theta is a circle with x-axis symmetry and radius a over 2. Cool. Do we want to look at these graphs?
It's okay. They have the link. They can do it.
All right, let's continue.
Limaçon.
Limaçon. That is a axon. I think it's called a circumflex. I could be totally wrong. If anyone here is taking French or is French or from a country that speaks French, let us know what that accent's called. I think it's called a circumflex. Limaçon. That's a soft C, not Limacon. Full width. Let's graph this. 3 plus 2 cosine theta. It is a little bit more difficult here to graph just point plotting. So let's draw this auxiliary graph, which is just going to be the 2 cosine graph shifted up 3. And then let's translate it to this graph. This little trick, this auxiliary graph, I think you'll see how powerful it is as we do more complicated things, but also
whoa, line tool.
Actually, shift. Did you know that?
Really?
I'm holding the shift key. I never went to the line tool. Okay, so we have 3 plus 2 cosine theta. So our midline is at, where's that going to be? 3, 2, 3, 4, 5. You know what? I'm going to redraw this x-axis down here.
Okay.
1, 2, 3, 4, 5. And then I'm like blanking on how to draw 3 plus 2 cosine theta. You know, it's because it's totally because it's not in the way I want to look at it. 2 cosine plus 3.
Start at 5.
Start at 5 and then go down to 1. All right. And so while I continue to draw this, Limaçon is it? Let me come back to that. Let me come back to that. So we have 2 pi. We're always going to graph an entire period, right? Depending on what that theta is. It's always nice to go all the way up to 2 pi. Pi over 2, 3 pi over 2. Let's get a pi over 4 in there. It's always nice. And then let's start to graph this. So we're going to be down here at pi. We're going to be at 3 at pi over 2. 3 at 3 pi over 2. Boom. And then can you figure out what that pi over 4 value is for me while I continue to graph this? Just so we have it ready.
Yeah.
2 cosine pi over 4 plus 3.
4.4142.
4142. 5, 3, 1. Okay. Let's translate this over to the graph. We're 5 at 0. Pi over 4, we're going to be at 4.4. And we're decreasing. And then we're going to be at 3 at pi over 2. We're still decreasing. We're decreasing all the way up until pi. And then, what is 3 pi over 4 going to be?
3 pi over 4.
And we can reuse these values for the other side.
That'll be 1.5858.
1.58, sweet. So at 3 pi over 4, we're at 1.58, about right there. We're decreasing, decreasing, decreasing. And then at pi, we are at 1. And then at 5 pi over 4, we're back at that 1.58. Right, so I want to zoom in real quick. This is a calculus question. But when I zoom in, specifically with this Limaçon that we're graphing here, as I approach this point, we're actually going to smoothly pass through it like a dimple. Think of someone that like smiles and you see like the smooth little spot in the dimple. It is a smooth transition. I want you to remember that because we're going to come back to that when we get to the other limacons. This is a dimpled limacon. We never actually get to the pole. Can you tell me why we never get to the pole?
Well, is there any point at which on our auxiliary graph we're going to be able to get to something that's a 0?
Nope.
Okay. So then our radius can never be 0.
Yeah. So we never pass through the pole because we never get a radius value of 0. Right. These are just little things I'm saying out loud that are going to play a role in a second when we start to look at different variations of this limacon. Getting bigger, and then was a 4.4. And I feel like I'm doing something wrong. I don't think I actually got to 4.4. There it is. Boom. And then that is kind of like a circle. It's a limacon, and it is a dimpled limacon.
Mm-hmm. I think it's well worth clicking on the Desmos one for this one.
Yeah, let's do it. Yeah, let's do it. Desmos, beautiful, free math. Boom. And if I just zoom in on there, I just want to make it clear that this is a smooth little transition. Look at that. Nice. All right. Before we continue on to the next one, we have our graph 3 plus 2 cosine theta. This is what it produced. If I give you A plus B cosine theta, what do you think is going to happen?
Well, I think a key part of this, the way that we got the dimpled limacon, so that we didn't end up getting to 0, was that our auxiliary graph never got us to 0, where the A value was greater than the B value.
Yeah. So if A is bigger than B, we're going to have a dimpled limacon. Notice in the next one, it has a new name, Cardioid. It is actually still a limacon, but it gets a special name. The A and the B are the same, so we'll see what happens there. I also, ooh, I like that. Ooh, I like that. Thank you. Smart. Okay, so A is bigger than B. That's what creates that dimple. How did we get all the way out to 5?
It's because we were looking at A plus B, and that was, and then the reason it's like on our horizontal part is because we're using cosine.
Yeah. So if it was sine, it would have been y-axis symmetry, and cosine would have been x-axis, just like with the circles. Right. And then how do we know where the dimple is in terms of its radial length?
Well, that was from our minimum on our auxiliary graph, right?
It's like A minus B, I think, right? Because with cosine, the max is negative, the min is -1. So we're going to subtract that value too. Right, cool. So the kind of the idea here is going to be advantageous when you start to do calculus with polar graphs, is that you look at 3 plus 2 cosine theta, just like you look at 2x plus 5, and you kind of know what it looks like. Right? 3 plus 2, that 3 is bigger than the 2, so we're never going to get to the pole. And I know my max, I know my symmetry. You can kind of know what the graph looks like just from the numbers given to you. That's a limacon, a dimple limacon. Here is a cardioid. Now look at that A and the B value. What do you notice?
They're the same. So whenever we have our sine theta outputting a -1, then we're going to end up with a radius of 0.
So let's see, we got 6. This is sine. Oh, so we're starting at the midline. Pi over 2, we get up to the max of 6. And then we're going to be at pi, min 2 pi. And then we got some other values in there. Let me go ahead and draw this auxiliary graph. Would you mind finding us what pi over 4 is?
Sure.
Thank you. This one's called a cardioid. See why in a second.
5.12.
5.12. Thank you. All right, so we start at 3, and this is sine. So we are starting at 3. That is not our max, though, like it was with cosine. And then a pi over 2, we're at 6. So we actually going pretty far out. And you said 5.12 at 5.4, or at pi over 4. 5.12. All right, so we're going like this. And then at 3 pi over 4, we're going to be also at 5.12. And then at pi, we're at 3. Right, we're in the ray in the direction of pi, 3 units out. I feel wrong graphing from pi to 3 pi over 4, but it feels easier on my hand. The graph is actually
easier to pull than to like push.
Yeah. All right, then at what is that value at? What is that going to be? 5 pi over 4. Yeah, I keep forgetting to
0.87.
Boom. And then on the other side, we're going to get 0.87 again. All right, and let's zoom in on this one. Here's what's happening with here's what's happening with the cardioid. All right, we're going to get to 0. And then we're going to immediately turn around. And we actually have a cusp for the cardioid. Cusp meaning there's an immediate change in direction. Did you is the polar graph for this one anywhere? Boom. Cusp, immediate. I don't see the polar graph for this one.
It's up a little bit more.
Is it just all, is it here?
Yeah.
Sweet. Wait, it's not there. Oh.
Let me change the color for this.
I have not granted myself permissions to draw on this. Tommy's being weird, guys. There it is. I see it. Yeah. I see it. Aha. And there it is. And look at that. Woo. We got our cusp. Like we can zoom infinitely close. It's just going to get more intense in terms of change in direction. Let's go ahead and toggle back over. Here we are. That is a cardioid. And there's a silly way to remember it that, I still remember from when I learned about polar graphs in high school. So apparently it's pretty good. But what do you think of when you think of cardio or cardioid?
Hearts.
Hearts. That is an upside down heart. It's kind of boring. But if you think cardioid, if someone says, hey, is that a cardioid? You can think, is there a cusp? Is there a heart shape going on? That's not as much the case for the limacon, the dimpled limacon.
Okay.
Mr. Stein never gives limacons as an exercise because he thinks they're ugly. One year he's like, why are you giving them limacons, like dimpled limacons? I'm like, oh, it's one of the shapes. And he goes, but they're ugly. Stop giving them. I never have them. I'm like, whoa. But anyways, dimpled limacons are great.
Yeah, I think dimpled limacons are cute.
I kind of like them. I kind of like the fact that they're smooth, unlike the cardioid that has a cusp. All right, we got one more type of limacon. And what do you notice about the A and B value here?
The A is less than the B, so we're gonna have some negative values. So maybe that's gonna make something interesting happen. Maybe throw us for a loop.
What else do you notice? Just about the one we've been given.
We have sine.
Sines.
So we're gonna have y-axis symmetry.
Y-axis symmetry. Something weird's someone's gonna throw us for a loop. Let's knock it out. Right. So we have 2 plus 4. So we're gonna have a midline of 2. Oh, this graph's gonna be blue. And then we have a 1, 2, 3, 4, all the way up to 6. 1, 2, all the way down to -2. Let me go ahead and get rid of that just for space reasons. We got pi, 2 pi, pi over 2, pi over 4, and then let's see, sine. So when we plug in 0, we get 0 plus 2. That's 2. We're gonna get all the way up to our max. back to our midline, down to our min, back up to our midline. Pi over 4 is going to be 2 plus 4 root 2 over 2. What's 2 plus 2 root 2?
4.8.
4.8. Awesome. And then let me actually ask for this one. What is 2 minus 2 root 2 for our 5 pi over 4 value?
Oh, sorry.
That's okay. 2 minus 2 root 2. We could probably use symmetry to get it too.
Yeah.
We're going up 2.8, so we're going to go down 2.8. Is it around negative 0.8?
Yeah, perfect.
Sweet.
Negative 0.8284.
Negative 0.8, positive 4.8. Cool. All right, so here's our auxiliary graph. And let's start graphing this up. All right, we're at 2. We are increasing to pi over 4, 4.8 comma pi over 4. 4.8. And then we get all the way up to 6. Then we start to decrease again, 3 pi over 4, 4.8, comma 3 pi over 4. Then we decrease again, we get to 2 at pi. And then this is actually interesting. When do we get to 0? Ooh, we kind of got to do a little bit of algebra.
It's like in the middle.
It's like in between pi and 3 pi over, and 3 pi over 4. 5 pi over 4. 5 pi over 4 is going to yield negative 0.8. So we're going to be right there. The question now is, at what point do we get to 0? Can we do that algebra real quick?
Sure. When
is the radius 0? So 2 plus 4 sine theta. Minus 2.
Mm-hmm. And then divide by 4.
Divide by 4, negative 1/2 equals sine theta. We can do that, right?
Mm-hmm.
Theta is equal to, when is sine negative 1/2?
7 pi over 6.
7 pi over 6 plus 2 pi k. And also, where's the other place? 11 pi over 6, yeah. Awesome. So actually, I'm going to go back to here. And I'm going to add a little dotted line. And that is, we just said 7 pi over 6, right?
Yes.
When we pass through the origin, we are going to be tangent to this pink line. Boom. And then let me zoom back out. We have at, what is that going to be? 3 pi over 2, we're at negative 2. So 3 pi over 2, we go in the opposite direction 2. And then at 7 pi over 4, we're going to be at negative 0.8. 7 pi over 4, negative 0.8. And then just like there was 2 solutions, we're going to have 2 tangent lines at 11 pi over 6. We pass through the origin, we'll be tangent. Boom. Let me go ahead and get the outer loop. Your pun was clairvoyant. There was a loop. This is a looped limason, dimpled limason, cardioid, cusped limason, and a looped limason. Boom. All limasons. I don't really know the etymology of limason or its translation.
Sounds like a good journal idea.
Yeah, I think so. You saw where I was going with that. Awesome. Hey, did you graph this one?
Yes, I think so. Just the blue dot. Do you see? Can you click on that and see?
I don't see anything there. Maybe you need to click out of it. No, but the dot's right there though. If I change to the arrow clicker, then it appears. That's weird.
Okay.
That's weird.
I also clicked on it and then clicked away
Boom.
from it.
Looped Lima-san. And then I'm actually going to add, hey, what is the polar equation for a line that goes through 7 pi over 6?
Theta equals 7 pi over 6.
Theta equals 7 pi divided by 6. And why is it not letting me do that? Oh, I think it doesn't like theta. Hey, what is the Cartesian equation? It's actually boom, and then tan, right?
Mm-hmm.
Tan of 7 pi over 6, and then x.
There you go.
Tangent, literally. The loop is tangent to. Boom.
Sweet.
Let's jump back. It keeps telling me to create a copy. I don't want to do that.
Whatever, Kami.
Yeah, Kami, why are you being weird today? All right, there we are. A looped Lima-san. What are some relevant geometric aspects of this shape?
It has y-axis symmetry, so we're working with sine. And we have a loop because we have a is less than b. Our max is at 6, where it's a plus b. And I guess our min is 0.
Like, no, the min is -2, right? Like we have like don't forget that just because it's not at the pole doesn't mean it's a min. A min is still -2 here.
But it's getting reflected up.
Yeah, yeah.
Okay.
How can you identify the size of the outer loop and the inner loops?
It's so the outer loop is gonna go up to 6 because that's a plus b. And then our inner loop is gonna be whatever our a value is.
No, I don't think it's gonna be whatever the a value. I think I can create something that won't. If I have like 3 plus 11.
Difference of our
I think it's the difference, right? 3 minus 11 would be -8. I think our loop would be -8 units.
That makes sense.
Yeah, boom. Looped.
And that would not fit on our graph.
That would not fit on our graph. No. All right. So Lima-san, circle, circle. We got 2 more shapes. 3 more problems, but 2 more shapes.
Do we want to do this one?
No, actually, let's skip this one. Okay. Do you know why I want to skip this one?
Because it's the same thing.
It's the same thing. And also, when we find that tangent line, it's not a fun number. Right. Tell me some stuff about this though before we move on.
X-axis symmetry because cosine. We're gonna have a loop because a is less than b. We're gonna go up to 5. Our inner loop is gonna be 1.
Yeah, so we could kind of just like do a quick sketch. Up to 5, inner loop at 1, and it's just gonna do this. No, it's not. What happens when you plug in pi?
Cosine of pi is.
Oh, it's gonna be -1, right?
-1. So then.
Yeah, so it's gonna look something like this. Kind of missed.
That's okay.
That's pretty dang bad. Anyway, let's go ahead and skip this one. All right. Roses. So how does this one differ from the ones we just did?
Well, we're multiplying our theta by something. So we're gonna get extra, I guess, extra periods.
Let's but we still want to graph up to 2 pi though.
Okay.
Because we want to graph a point all the way around, which requires us to get to 2 pi.
Okay.
So while this is going to have a period that is only 1 pi, let's graph 2 periods.
Okay.
Oh, you got me. Thank you. Let me delete what I had. All right, so
I can get rid of these.
We want to go up to 5. Yep. And it's sine. So we're going to start at the origin. And then we're going to be way up here. That's not even true. At pi over 4, we're going to be way up here. Boom, boom, boom. And then we're graphing all the way to 2 pi. So let's go back up here and get our second period. Okay, so point plotting time, we got 0. At pi over 4, we are at, what is that, 5? Right? And we're increasing all the way up there. We immediately start to decrease. And at pi over 2, we're going to be back at 0, which actually means we're going to be tangent to pi over 2 at 0, by the way. Boom. Coming down. So I'm actually going to put some arrows on here so we can kind of like identify the path that this graph is taking. This is actually going to be very relevant in the next video. And then at 3 pi over 4, we are at -5. We are decreasing to it. Then we're increasing to pi, which will be at 0 again. We are increasing. And then this is why we're going all the way to 2 pi, because now we are graphing third quadrant angles with positive radial lengths. So we are going to be in the third quadrant now. 5 pi over 4 is going to give us 5. And now you can start to see why it's called a rose. At 3 pi over 2, we're at 0. At 7 pi over 4, we're at -5. We are even though I'm going up visually, we are decreasing right now. Weird to think about. And then we are increasing, even though I'm going down, back to the origin. Boom. R equals 5 sine 2 theta is a rose petaled graph. Although I don't think roses have petals like that, do they? Hey, maybe they do. If you like actually pluck a rose petal out.
I don't know.
Yeah.
What do you mean? Like, are they oblong like that? Or...
Yeah. I don't know.
I think they're more on like the more like rectangular side of things. Like this looks more elliptical. This more looks like daisy petals or something. Or black-eyed Susans.
Yeah, they're more like, yeah, you're totally right. All right, let's jump back. Boom. Boom. Cool. All right. So this is what happened. We started at the pole and we moved up, we came down, and then we went into the fourth quadrant because our radius was negative. And then we went into the third quadrant. And then we went into the second quadrant because our radius was negative. And then we found our way back, and then we will repeat with every 2 pi.
So we have 4 petals. Wonder where like that 4 can come from what we're looking at in our equation.
Let's hold that thought. Let's look at the next one. 5 sine 2 theta, 5 cosine 3 theta. Also, think about sine and cosine in symmetry, by the way. But let's do the next one and then come back to that question you said. We have 4 petals. Where is the 4 coming from? I don't know how many 4. All right, anyways, let's knock out this one. 5 cosine 3 theta. All right, so this one's a little bit weird. We're going to have a period of 2 pi over 3, right?
Mm-hmm.
So pi over 4, pi, this is 3 pi over 4. 2 pi over 3 is before 3 pi over 4. It's right there. So we're going to have done an entire, and actually it's cosine, so we're going to be at the peak. Boom, boom. All right. So what's halfway between 2 pi over 3 and 0? Pi over 3?
Pi over 3.
Yeah. That's going to go right there, right?
Mm-hmm.
Pi over 6 is right here just for the sake of it. I think we might actually use it. We're going to be at the bottom here. Oh, you know what? Maybe not. What's halfway between pi over, oh no, pi over 6. Yeah.
Yeah.
So actually it's a little bit closer to pi over 4. My graph's not the best. So it's okay. So at pi over 6, we're going to be at the at 0, right?
Mm-hmm.
And at when are we going to be at the origin again? At the 0 value again?
Pi over 3 plus pi over 6, which is what?
Pi over 2, right?
Yep.
Yeah. Just going to go through that. All right, and we're going to do this 3 times. All right, so let me go ahead and get those values. We're going to be back here. Let's do, help me out here because this is kind of a struggle.
So our next like period is happening at 4 pi over 3.
4 pi over 3. So that's going to be, here's 3 pi over 2. Here is 5 pi over 4. 4 pi over 3 is like right here.
Okay, looks good.
Cool. So that's going to be up there, right?
Mm-hmm.
All right, so halfway is going to be between 2 pi over 3 and 4 pi over 3 is
pi?
3 pi over 3, yeah. That's kind of nice.
Mm-hmm.
Which makes sense because of the bottom. Boom. We have 1.5 of our 3 periods and we're at halfway. Sweet. And then how about what's halfway between 4 pi over 3 and 6 pi over 3? 5 pi over 3?
5 pi over 3.
I'm just going to put a 5 pi over 3 here. This is probably not the best way one could have drawn this, but it is the way that I did it. All right, so we start at 5. Awesome. We get down to pi over 3. So at pi over 3 is when we get to the origin. So I'm going to kind of come out a little bit.
At pi over 6 is when we get to the origin.
Pi over 6 is when we get to the origin. Thank you. Pi over 6. I'm going to draw a little dotted line there. Thank you for catching that. This is
that would have been a disaster. Because then we would be doubting ourselves the rest of the time.
We really would be. I'm like, why is it not symmetric? Okay, and then we get
at pi over 3, we get -5.
Boom. So awesome.
So we're kind of doing this arc.
Yeah,
okay?
I like that.
But then we're going to go back around.
And then
we got to hit 0 at pi over 2.
0 at pi over 2. So kind of here's the pi over 2 line. We're going to be tangent to it when we hit 0. Nice.
Okay. And then we go back up to 5 at, was that 2 pi over 3?
I think so.
But then we're going to come back down to 0 at, was that 5 pi over 6? I guess we didn't write that down, but
yeah.
From our brains, we can get that.
And from symmetry, right?
Mm-hmm.
That's the beautiful thing about these graphs is they're very symmetric. And that's why we're able to so easily. Okay. And then
we got to keep going. So that we get to
pi, we're at -5
and pi, and that makes sense. And then we closed it. Oh,
we closed it. Halfway through this thing, we closed it.
Huh.
So we got the number 3 and we closed the loop halfway. For the 2, we didn't close the loop halfway. We continued to make more loops. But when we had the 3, we closed the loop. Let's go back to that question that you asked earlier. How do we know that we're getting 4 loops, and how do we know that we're going to get 3 loops? What do you think the rule here is?
Well, you're talking a lot about symmetry, right?
Mm-hmm.
And how symmetry is really important for how we're thinking about these.
Okay.
So maybe it has to do with like if we're looking at y-axis symmetry or x-axis symmetry. Or if like our auxiliary function is even or odd. Auxiliary graph.
I think it's all about like how many periods do you have within 2 pi? If you have an even number of periods within 2 pi, then you're not going to close the loop. If you have an odd number of periods within 2 pi, when you get to this point down here, you're going to be at pi, but you're going to have a negative value. So you're going to be where you started. Whereas up here, when we're halfway, or maybe not halfway, but these 2 points right here and here are different coordinates. These 2 points right here and right here are the same coordinate. So I think it's about that the even or oddness of that coefficient. It's like here we have R equals A sine B theta. And down here we also have A sine B theta. I think if B is even, how many petals are we going to have?
We're going to have twice as many petals as B's.
And then if B is odd,
we're getting B petals.
B petals. Let's test this theory in Desmos.
Okay.
Desmos, beautiful, free math. So R equals, let's go with 5. Ooh, that's a nice number. Cosine. Let's actually do this. A theta. Let me throw some parentheses around there. Let me add a slider. So if A is 1, we have a circle with one petal.
Like one petal, I guess, yeah.
Right, if A's, whoa, now activity for your journal, play around with sliders and polar graphs. Let's go to 2 though.
You should make them integers.
Yeah, just so we're not like struggling.
It's very confusing.
1. Sweet, okay. All right, so 2, 4 petals, 3, 1 petal.
3 petals.
4, 8 petals. 5, 5 petals. 6, 12 petals. 7, 7 petals. Boom, boom, boom. So it is that the closing of the loop with odd periods. I'm going to even make it negative. Oh, you know what? Cosine of negative theta is just cosine theta, so nothing else changes. That's kind of boring. Yeah, that's cool. All right, cool and boring at the same time. Boom, there we go. That is the pattern there. So like, let me do this. Let me scroll back up to the top, or let me add another page. I have a few questions for you, and then we'll close this video out. We'll do 2. We'll do 2. Here we go. Here's a polar graph. Tell me about it. Let's go 2 plus 4 cosine theta.
Okay, so we have A plus B cosine theta. So that means that we're looking at some sort of Lima sum with the circumflex. Thank you. And then we have cosine, so it's going to have x-axis symmetry. And since A is less than B, we're going to get, it's not going to be a dimple. It's not going to be a cardioid. It's going to be the other one. What do we call that?
I just called it a loop. I don't know if that's
technical,
but that's what I call it. Loop.
The max is going to be at 6. Our inner loop is going to be 2.
How do you spell outer?
O-U-T-E-R.
Just 1 T? Boom. Sweet. I think that's pretty much all we need to say about that. How about R equals 47 cosine 11 theta?
Okay, so it's going to be a rose because we're multiplying our theta by something. Since 11 is odd, we have 11 petals. Cosine gives us x-axis symmetry, and 47 is going to be like the length of each of our petals, which is obnoxious.
I mean, compared to a billion, it's a pretty small number.
That's true.
Should I call it petal length? Maybe
Sure.
Petal radius, whatever. Petal length, 47 units. I got one more for you, actually. I said 2, but I want to do a third one.
Okay.
How about R equals 2 plus 5 cosine 3 theta?
Oh, interesting. So This makes me think that we're going to have multiple petals in a Lima song.
So how many petals are we going to have?
We're going to have 3 petals if we're going with our rule from before.
Okay. Let's see if we're right at the end, by the way. I don't know what it's going to look like.
We're going to have a max value of 7. We're going to get like loops in our petals.
Yeah. I think so. What's the min here?
3?
Yeah, 3. Min -3. So actually I have graphed this before. I don't know if this one exactly, but I like to call it a Lima Rose. Let's look at what it looks like. So 2 + 5 cosine 3 theta. Let's see if your observation's right. 2 + 5 cosine 3 theta. Look at that.
Whoa.
It is a three petals, technically. I guess 6 petals if you count the ones inside.
3 petals with 3 inner loops.
With 3 inner loops. Nice. I wonder what happens if we make this number even. Whoa.
That's pretty cool.
And what if we make it sine? Will those inner loops be within the no? Look at that. Alrighty.
Wait, that's weird because it doesn't have y-axis symmetry.
I don't know what I do. How do I get back?
There you go.
Yeah.
Strange. You should do an art project.
Yeah. Oh, you just decided the unit project for this unit. Awesome. And there'll be complex numbers involved too. All right, there we have it. Let's close this one out. What's your favorite Pokemon?
I really like Turtwig. It's just like really cute.
Turtwig is pretty great.
What's yours?
Let me think for a second. So there's a website, and I'll send it to you, that asks you probably like 200 questions. But the questions are all the same. It's like a list of 5 Pokemon, and you pick your favorite from that list. And then as you proceed through, you start to see Pokemon that you've said you liked before. And the algorithm outputs your favorite Pokemon. And I did it recently, and I got this is going to be a curveball. I got Politoed.
Whoa.
And Politoed's pretty great.
Wait, didn't you say your like brother's favorite Pokemon was Politoed at some point or something like that?
Yeah, he is a Buizel. You know Buizel?
No.
You don't know Buizel? Anyways, let me probably should close.
I also very seldom say Pokemon names out loud.
I totally said that is Buizel.
Are you sharing your screen? Because I just
I'm not. Boom, Buizel.
Oh, okay.
Yeah. But yeah, my brother's favorite Pokemon is Politoed. I got Politoed. I might have been like, he sent me the thing, so I might have been like cognitively thinking about. So it's obviously not going to be the most reliable piece of data, but I like to think my favorite Pokemon is Charmander.
Charmander's pretty cool.
Although I'm a big fan of Krabby now. Krabby and Kingler. All right, let's close this one out. Cool. Ready?